This is part 6 of the airfoil section of our aeronautical engineering course. The lift and drag coefficients are used to calculate the lift and drag on an airfoil at any given angle of attack. Air density, wing area, and velocity must also be known. The lift formula is lift equals coefficient of lift times that Greek letter rho stands for air density, that A stands for wing area, V is velocity, so velocity squared over 2. Okay, the Clark-Y airfoil table on page 5 indicates that the maximum lift coefficient for this airfoil is seen at a 14.7 degree angle of attack, and that lift coefficient would be 1.325. Okay, if the area of this wing is 160 square feet, and the velocity of the wing is 47 knots, and we're talking about standard atmospheric conditions, so the rho is equal to 1.225 kilograms per cubic meter, then how much lift will be produced by the airfoil? Okay, first we must know that we need to know how to turn our 160 square feet of wing area into square meters, and we need to convert our 47 knots into meters per second. 1 foot is 12 inches. 1 square foot is 12 inches times 12 inches. 1 inch is 2.54 centimeters. 1 square inch is 2.54 centimeters times 2.54 centimeters. 1 centimeter is 1/100th of a meter. So 1 square centimeter is 1/10,000th of a square meter. 1 knot is 1 nautical mile per hour. Nautical mile is approximately 1.15 statute miles. A statute mile is 5,280 feet. So when your speedometer on your car says 55 miles per hour, that's 55 statute miles per hour. Those 5,280 foot miles. A more accurate description is 1 nautical mile approximately equals 6,076 feet. Wikipedia defines a nautical mile as exactly 1,852 meters. So the lift produced by a 160 square foot Clark-Y airfoil moving at 47 knots in standard conditions at a 14.7 degree angle of attack is all these numbers. Okay, let's turn our 160 square feet into meters. I told you right here it's 14.86, but here's how we figure it up. Okay, we multiply the number of feet squared we have times inches squared per foot squared. There are 12 inches per foot, so there are 144 square inches per square foot. So multiplying that times that gives us the number of square inches that we have. Multiplying it times that turns our square inches into square centimeters. Okay, and then dividing that by 100 a couple of times turns our square centimeters into square meters. So if we take our calculator and we punch up 160 times 12 times 12 times 2.54 times 2.54 equals divided by 100 equals divided by 100 again equals, we get 14.86 meters squared. Okay, don't let this dimensional analysis scare you. It's really simple. We could just look at something we're more familiar with. Let's say each porch in the world has 2 dogs per porch. Okay, and let's say each house has 2 porches. And let's say there are 10 houses on each block, and there are 50 blocks in each city, and there are 200 cities in each state, and 50 states in the country. So we'll just multiply our 2 times our 2 times our 10 times our 50 times our 200 times our 50, and we'll calculate that there are 20 million dogs per country. How do we do this? Well, we use dimensional analysis. 2 dogs per porch times 2 porches per house gives us 4 dogs per house. We have porches on top, porches on bottom, so we can just draw a line through our porches. Okay, because porches divided by porches is equal to 1. So we have 4 dogs per house. Well, we have 10 houses per block, so we got houses on the top, houses on the bottom. We have 50 blocks per city. We got blocks on the top, blocks on the bottom. We got 200 cities per state, so we got cities on the top, cities on the bottom. We got 50 states per country. We got states on the top, states on the bottom. So what we're left with is 2 times 2 times 10 times 50 times 200 times 50 dogs per country, or 20 million dogs per country. We turn our 47 knots into meters per second. We just multiply 47, well, a knot is a nautical mile per hour by definition. Well, there are 1,852 meters in a nautical mile, so we multiply our 47 times 1,852 and we'll get meters per hour, because our nautical miles will cancel out. And we divide that by 3,600, or multiply it all times 1 hour divided by 3,600 seconds, and we'll turn our meters per hour into meters per second, and our answer is 24.18 meters per second. Okay, I didn't remember that 1,852 meters is a nautical mile, but I do remember the centimeters and inches and feet. If you wanted to figure it that way, you could say 47 nautical miles per hour times 6,076 feet per nautical mile times 12 inches per foot times 2.54 centimeters per inch divided by 100, because you have 1 meter per 100 centimeters. Okay, times 1 hour per 3,600 seconds, and that'll give you the same number, 24.18 meters per second. Getting back to our lift equation, okay, we just saw how we turn our square feet into square meters and turn our knots into meters per second. So we're ready to go. We've got the units we want. So our lift is going to be, our coefficient of lift, 1.325 times our air density, 1.225 kilograms per cubic meter. Let's just write 1.225. We'll write all of our units down here after our numbers. Okay, our wing area is 14.86 square meters, or meters squared. Our velocity is 24.18 meters per second, so we put a square up there because it's that squared. Now our units are going to be kilograms per cubic meter for air density. Okay, meters squared for wing area, and meters squared per second squared for velocity squared. So what we're left with is, well, meters squared times meters squared is meters to the fourth. Meters to the fourth divided by meters to the third is going to be meters to the 1 power, which is just plain old meters. So what we have is kilogram meters per second squared. Okay, kilogram meters per second squared, which is defined as a Newton, named after Sir Isaac Newton. Okay, so multiplying all this out, well, let's do it. Let's see, 1.325 times 1.225 times 14.86 times 24.18 times 24.18 equals, divided by 2, equals 7,051. Of course, I wrote 7,053 because I figured it out using the exact number of meters per nautical mile, but that's close enough. 7,050 newtons. Okay, how much is a newton? Well, a newton is a kilogram meter per second squared. So if a kilogram is here at the surface of the Earth subjected to the gravitational field of the Earth, which is 9.8 meters per second squared, 1 kilogram is going to weigh 9.8 newtons. Okay, well, a kilogram is about 2.2 pounds, so 2.2 pounds equals 9.8 newtons. So if we take our 7,053 newtons that we calculated, multiply it times 2.2 pounds and divide it by 9.8 newtons, we'll get 1,586 pounds. That's the lift on our wing. More accurate numbers for a conversion factor of 1 pound equals 4.44822216 newtons. That's not the sort of thing anyone remembers. You just Google it and find it out. And a newton consequently is 0.224808943870961 pounds, but who really needs to be that precise? Okay, apparently the wing of a Cessna 150 has a lift coefficient close to 1.325 because it matches up to our problem pretty closely. Its wing area is 160 square feet. Its stall speed without extended flaps is 47 knots when fully loaded to 1,600 pounds. 1,586 pounds is what we figured our lift was on this Clark Y airfoil under the same conditions. So as you can see, these numbers are very close to the numbers of our Cessna 150 numbers are very close to the numbers of our sample problem. The drag equation is almost identical to the lift equation. The only difference that you substitute the coefficient of drag for the coefficient of lift. All the other stuff's the same. The density, the wing area, the velocity squared. So the air density, wing area, and velocity, yeah, they're all the same. The table on page 5 shows that at a 14.7 degree angle of attack, that's the angle of attack that we got our coefficient of lift of 1.325. At that same angle of attack, the drag coefficient is 0.1399. So if we just multiply this 1,586 pounds times 0.1399 and divide it by 1.325, the ratio of our drag to lift, we'll get 167 pounds of drag. So there is the last of our airfoils lessons.